Introduction: the hidden environmental cost of military technology. In the rapidly evolving landscape of modern warfare, technological superiority has become the cornerstone of military effectiveness. From stealth fighters to precision-guided missiles, these innovations represent the pinnacle of human ingenuity in defense technology. Yet beneath this impressive technological advancement lies a growing environmental concern that remains largely unaddressed: electronic waste generated by military operations. The intersection of cutting-edge military technology and environmental sustainability presents one of the most complex challenges of our time. While advanced technology enables military success, the resulting electronic waste creates a significant environmental burden. Unlike consumer electronics, military hardware operates at the technological frontier, utilizing specialized components designed for extreme reliability and performance. These requirements necessitate rare materials, sophisticated manufacturing, and frequent upgrades, all factors contributing to a massive e-waste footprint. This analysis examines the full scope of military e-waste, from its composition to its environmental impact and emerging solutions. The composition of military e-waste, a treasure trove of critical materials. Military e-waste represents a unique category of electronic waste due to its extraordinarily high concentration of valuable materials. Defense electronics contain significant amounts of precious metals including gold, silver, platinum, and palladium, essential for ensuring performance under extreme conditions. Gold plays a crucial role in military electronics, particularly in connectors and circuit boards where its excellent conductivity prevents system failure. Silver appears prominently in missile guidance systems and radar equipment, providing superior electrical performance in critical situations. Platinum serves as a key component in high-performance sensors and catalytic devices that enable precision targeting. Palladium is essential in multi-layer ceramic capacitors that populate virtually every circuit board in military equipment. Beyond these precious metals, military e-waste contains a complex mixture of other valuable and hard-to-source materials. Rare earth elements such as neodymium and dysprosium enable the high-strength magnets in motors and guidance systems that give modern weapons their precision. Specialized military-grade alloys containing cobalt, tungsten, and molybdenum provide essential properties for aerospace applications and weapons systems. Critical semiconductor materials including gallium arsenide and silicon carbide power advanced radar systems and electronic warfare equipment. The concentration of these materials makes military e-waste both a significant environmental concern and a valuable resource recovery opportunity. A single F-35 fighter jet contains more gold than 80 typical smartphones and more rare earth elements than 500 laptop computers. The e-waste footprint of modern military assets. The Australian Defence Force operates sophisticated military platforms that each generate substantial e-waste throughout their life cycle. Advanced aircraft systems. The F-35 Lightning II Joint Strike Fighter represents aviation technology at its peak but generates approximately 1.52 tons of e-waste per aircraft. This waste comes from its advanced avionics suite, sophisticated radar systems, and integrated communication equipment designed for battlefield superiority. The distributed aperture system alone, comprising 6 infrared cameras providing 360-degree awareness, contains numerous high-value electronic components requiring specialized disposal. The P-8A Poseidon maritime patrol aircraft similarly produces substantial e-waste from its sophisticated mission computers and sensor arrays. Each P-8A deployment releases dozens of sonobuoys, self-contained sensor systems that become marine e-waste after their brief operational life. The EA-18G Growler, Australia's electronic warfare aircraft, creates approximately 1.5 tons of e-waste throughout its service life. This specialized platform features the most advanced electronic systems in military aviation, including tactical jamming technology containing sophisticated components with unique recycling challenges. Naval platforms. Hobart-class air warfare destroyers represent floating electronic fortresses with a significant technological footprint. Each vessel generates 3-5 tons of e-waste during major system upgrades, with the Aegis combat system contributing significantly to this total. Collins-class submarines rely extensively on advanced electronic support measures and sonar systems, contributing an estimated 24 tons of e-waste per vessel. The Royal Australian Navy's future Hunter-class frigates will likely increase this e-waste footprint substantially as they incorporate ever more complex electronic systems, missile systems and smart munitions. Modern precision-guided weapons represent a growing source of military e-waste due to their sophisticated electronics and limited shelf life. The AGM-158 Joint Air-to-Surface Standoff missile generates approximately 100,200 kilograms of e-waste, primarily from its guidance electronics and infrared seeker. The BGM-109 Tomahawk cruise missile produces an estimated 200,300 kilograms of e-waste, containing both valuable metals and potentially hazardous materials. Even smaller systems like the Javelin anti-tank missile generate 50,100 kilograms of e-waste with sophisticated electronics requiring proper disposal protocols. Ground-based systems. The Jindalee Operational Radar Network represents one of Australia's largest sources of military e-waste, generating an estimated 5.8 tons during major technology refreshes. As Australia's over-the-horizon radar system, JORN relies on extensive electronic infrastructure spread across multiple remote sites. The ADF's growing inventory of unmanned vehicles, battlefield sensors, and tactical communication systems adds further to this e-waste burden. Thousands of individual electronic devices deployed across training and operational environments eventually require specialized disposal. Environmental impacts beyond the battlefield. The environmental consequences of military e-waste extend far beyond simple landfill accumulation, presenting multifaceted challenges. Toxic materials and contamination. Without proper handling procedures, toxic materials from military electronics can leach into soil and groundwater systems, creating long-term environmental hazards. Military-grade components often contain beryllium oxide in radar systems, which can cause severe lung disease if improperly handled. Cadmium in specialized batteries and coatings presents serious risks to soil and water quality when improperly disposed. Hexavalent chromium in corrosion-resistant coatings has been recognized as a potent carcinogen requiring careful management. Brominated flame retardants in circuit boards and casings can persist in the environment for decades after disposal. These contaminants can migrate through watersheds, affecting ecosystems far from their original disposal locations and potentially entering the food chain. Resource depletion concerns. The loss of precious and rare earth metals through improper disposal of military e-waste contributes to the depletion of finite global resources. Global reserves of indium, essential for infrared sensors and displays, could be depleted within 20 years at current consumption rates. Rare earth elements used in guidance systems face significant supply chain vulnerabilities due to geopolitical factors. Platinum group metals used in sensitive electronics represent a non-renewable resource with extremely limited global distribution. The defense sector's high standards often require virgin materials rather than recycled content, intensifying resource pressure. Without effective recycling, these valuable materials are permanently removed from the industrial ecosystem, increasing scarcity. Carbon footprint considerations. The energy-intensive production of high-tech military components significantly contributes to carbon emissions throughout the supply chain. Manufacturing a single semiconductor chip for advanced radar systems can require up to 2,000 times its weight in fossil fuels and chemicals. The production process demands thousands of liters of ultra-pure water and significant energy inputs for precision manufacturing. When military electronics are discarded rather than recycled, this embodied energy is wasted, and new production must begin with raw materials. This multiplies the carbon impact of defense systems beyond their operational footprint. Technical challenges in processing. The specialized nature of military electronics creates unique challenges for recycling efforts unlike those in consumer electronics. Military systems often feature hardened components designed to withstand extreme conditions, making separation more difficult. Custom-designed parts with limited documentation complicate identification and proper handling during recycling. Security-classified technologies require specialized handling to prevent unauthorized access even during disposal. Composite materials that are increasingly common in defense applications complicate separation processes. These factors make conventional e-waste recycling methods insufficient for military applications, necessitating specialized approaches. The sustainability frontier, innovative approaches. Despite these significant challenges, there's a growing commitment within defence organisations to address environmental impacts. The Australian Defence Force is increasingly exploring methods to minimise its environmental footprint while maintaining operational effectiveness. Strategic initiatives for military e-waste management. Implementing comprehensive e-waste recycling programs can effectively recover precious metals while reducing landfill waste. The ADF has the opportunity to establish world-leading practices through dedicated military e-waste processing facilities. Systematic tracking of electronic components throughout their life cycle would enable better end-of-life management. Collaboration with metallurgical specialists could develop advanced recovery techniques specifically for defense applications. International partnerships would allow sharing of best practices in military e-waste management across allied nations. Advocating for designs that facilitate disassembly can significantly ease the recycling of valuable components. This design for disassembly approach includes standardization of connectors and reduced use of proprietary fasteners. Clear marking of materials and hazardous components simplifies the recycling process at end of life. Modular design principles allow for targeted upgrades without complete system replacement. Investing in modular systems enables targeted upgrades without requiring complete platform replacement. The F-35's block upgrade approach allows software and selected hardware updates without full system replacement. Modular mission payloads for unmanned vehicles extend their useful life through technology insertion. Open architecture computing environments in naval vessels permit easier updating of electronic systems. Technology insertion programs for radar and electronic warfare systems reduce overall e-waste generation. Emerging technologies and approaches. Urban mining represents an emerging concept that seeks to recover precious materials from e-waste rather than extracting virgin resources. For military applications, this includes hydrometallurgical processes specifically adapted for defense electronics. Bioleaching techniques using specialized microorganisms can extract metals from complex circuit boards. Supercritical fluid extraction offers promising methods for recovering rare earth elements from composite materials. Automated disassembly systems are being developed for handling the complex military components that resist manual processing. Advanced separation technologies now make it possible to recover over 98% of precious metals from circuit boards. This creates a compelling economic case for recycling high-value military electronics beyond environmental benefits. Collaboration with recycling specialists is essential for developing best practices in military e-waste management. These partnerships can leverage academic research on novel recovery methods to solve defense-specific challenges. Commercial recycling expertise can be adapted to meet the unique requirements of military hardware. International standards organizations are developing best practices that balance security concerns with environmental needs. Indigenous knowledge in sustainable resource management offers valuable perspectives on responsible materials stewardship. Case studies: global leaders in sustainable military operations. Several nations and organizations are pioneering approaches to military sustainability that offer valuable lessons. The U.S. Department of Defense Sustainability Initiatives. The U.S. military, as the world's largest institutional consumer of energy, has implemented several innovative programs. The Defense Logistics Agency Precious Metals Recovery Program recovers over $3 million annually from military e-waste. The Navy's Ship-to-Shore Recycling Program has increased materials recovery from decommissioned vessels by 40%. The Air Force's Sustainable Technology Evaluation Program tests new recycling technologies specific. The European Defence Agency Circular Economy Approach. The EDA has developed a comprehensive framework for military circularity across European forces. The Circular Defence Initiative coordinates efforts across 11 European militaries to standardize recovery practices. Standardized demilitarization protocols ensure maximum resource recovery while maintaining security. Shared research funding advances specialized recycling technologies with broader application potential. Cross-border material recovery facilities achieve economies of scale impossible for individual nations. Norway's Green Fleet Initiative. Norway's defense forces have established a model program for electronic systems management worthy of emulation. Comprehensive life cycle tracking of all electronic components allows planned recovery of valuable materials. Strategic partnerships with specialized recycling firms ensure proper handling of sensitive materials. Advanced pre-processing facilities for classified materials protect security while enabling recycling. Remanufacturing programs for communication equipment extend useful life and reduce procurement needs. The path forward, recommendations for the ADF. As Australia continues to modernize its defense capabilities, effectively managing military e-waste becomes increasingly critical. Each new advanced system brings complex recycling challenges, but also represents opportunities for innovation. Policy recommendations. Establish a dedicated military e-waste management office within the ADF with specialized expertise and resources. Develop a comprehensive e-waste assessment methodology to accurately quantify the ADF's electronic footprint. Implement mandatory recycling targets for major defense contracts, with performance incentives for contractors. Create a specialized secure facility for processing classified and sensitive electronic components. Establish an innovation fund for developing Australia-specific military recycling technologies that address unique challenges. Technical approaches. Implement blockchain-based tracking systems for all electronic components to enable complete lifecycle management. Develop specialized pre-processing techniques for military-grade composite materials that resist conventional recycling. Establish a research program focused specifically on rare earth element recovery from defense systems. Create standardized demanufacturing protocols for common military electronic systems to improve efficiency. Develop sealed bid auction systems for recovered precious metals to maximize return on investment for the ADF. Industry collaboration. Establish a defense sustainability consortium bringing together military, industry, and research partners. Create knowledge-sharing mechanisms that protect classified information while enabling recycling best practices. Develop certification programs for contractors handling sensitive military e-waste to ensure proper procedures. Implement supplier incentives for designing easily recyclable electronic systems from the beginning. Establish mentoring programs connecting defense industry with sustainability experts to build institutional knowledge. Measuring success, metrics for sustainable defense. Effective e-waste management requires clear metrics and continuous assessment throughout implementation. Key performance indicators should include percentage of precious metals recovered from decommissioned systems. Reduction in virgin material requirements for new systems demonstrates closed-loop material success. Total lifecycle carbon footprint of major defense platforms provides a broader sustainability measure. Economic value recovered through recycling operations can help offset program costs. Toxicity reduction in disposal processes protects both environment and personnel handling materials. By establishing baseline measurements and setting ambitious targets, the ADF can track progress systematically. Conclusion: securing a sustainable future. By addressing military e-waste head-on, the Australian Defence Force can reduce its environmental footprint while recovering valuable resources. As technological innovation accelerates, balancing national security with environmental integrity becomes one of modern defence's defining challenges. For both military strategists and environmental advocates, the intersection of defense technology and waste management represents a critical frontier. This domain bridges cutting-edge innovation with essential environmental stewardship, working toward a harmonious future. Addressing military e-waste, from fighter jets to precision missiles, requires collaboration among defense forces, technology developers, and environmental specialists. This partnership has the potential to redefine our approach to defense, demonstrating commitment to both security and sustainability. The path toward a more sustainable defense posture requires vision, innovation, and unwavering commitment. By embracing the challenge of military e-waste, Australia can demonstrate that environmental responsibility and national security are complementary imperatives. The technologies that protect our nation today must not compromise the environment that sustains us tomorrow. Our approach to military e-waste will serve as a testament to our values and commitment to future generations.